Introduction. It is very difficult to define what the electric charge is. The word electric is derived from the Greek word electron, meaning amber. The existence of charges were known when charged particles were produced by rubbing due to friction of suitable materials. These facts are demonstrated by simple experiments. A. Suspend a glass rod rubbed with silk. Bring another glass rod rubbed with silk nearer to the suspended rod. It is observed that the suspended rod will swing away, showing repulsion. B. Similarly, suspend a plastic rod rubbed with fur and bring another plastic rod rubbed with fur closer to it. We observe that the rods repel. C. Again, if we suspend a glass rod rubbed with silk and bring a plastic rod rubbed with fur nearer to the glass rod, we observe that the rods attract. From the above, we find that glass rod rubbed with silk acquires something different from that of plastic rubbed with fur. That something is called charge. Unlike charges attract, like charges repel. By convention, the charge on the glass rod when rubbed with silk is positive and the charge on the plastic rod when rubbed with fur is negative. It is due to mechanical friction that the electrons are torn from the atoms. In the previous concept you studied electric charge. In this concept you study about conductors and insulators. Conductors and insulators. A metal rod held in hand and rubbed with wool will not show any sign of being charged. However, if a metal rod with a wooden or plastic handle is rubbed without touching its metal part, it shows signs of charging. Suppose we connect one end of a copper wire to a neutral pith ball and the other end to a negatively charged plastic rod. We will find that the pith ball acquires a negative charge. If a similar experiment is repeated with a nylon thread or a rubber band, no transfer of charge will take place from the plastic rod to the pith ball. Why does the transfer of charge not take place from the rod to the ball? Some substances readily allow passage of electricity through them, others do not. Those which allow electricity to pass through them easily are called conductors. They have electric charges, electrons, that are comparatively free to move inside the material. Metals, human and animal bodies, and earth are conductors. Most of the non-metals, like glass, porcelain, plastic, nylon, wood, offer high resistance to the passage of electricity through them. They are called insulators. When some charge is transferred to a conductor, it readily gets distributed over the entire surface of the conductor. It contrasts if some charge is put on an insulator. It stays at the same place. When we bring a charged body in contact with the earth, all the excess charge on the body disappears by causing a momentary current to pass to the ground through the connecting conductor, such as our body. This process of sharing the charges with the earth is called grounding or earthing. Earthing provides a safety measure for electrical circuits and appliances. There is a third category called semiconductors, which offer resistance to the movement of charges, which is intermediate between the conductors and insulators.
Before we get on with the video, hit subscribe and press the bell icon next to it to get instant notifications of our latest uploads.
Charging by induction. In the previous section we saw how a body is charged by friction. Let us now see how we can charge a metallic sphere by induction. Figure A shows an uncharged metallic sphere supported on an insulating rod. A negative charged plastic rod is brought close to the sphere. Free electrons in the sphere move away due to repulsion and piles up at the other end of the sphere. The near end becomes positively charged due to deficit of electrons. This distribution of charge ceases when the net force on the free electron inside the metal is zero, and this happens instantly. When the sphere is connected to a conducting wire, if it gets earthed and the electrons flow to the ground and the positive charge remains there due to the attractive force of the external charge. When the external conductor is removed, the positive charge remains in the sphere, making it a positively charged object. When the plastic rod is removed, the positive charge gets distributed uniformly over the sphere. Similarly, if a positively charged rod is brought closer to a sphere, the sphere acquires negative charge. Note: in this case, electrons will flow from the ground to the sphere. Basic properties of electric charges. If a system consists of 2-point charges Q1 and Q2, then the total charge of the system is given by adding Q1 and Q2. Thus, the charge add up like real numbers, scalars. Now we add charges, one should take care of its sign. Subtopics: Additivity of charges, Conservation of electric charge, Quantization of electric charge, Additivity of charges. If a system contains 2-point charges Q1 and Q2, the total charge of the system is obtained simply by adding algebraically Q1 and Q2. That is, charges add up like real numbers, or they are scalars like the mass of a body. If a system contains n charges Q1, Q2, Q3 and so on, Qn, then the total charge of the system is Q1 plus Q2 plus Q3 plus and so on plus Qn. Charge has magnitude but no direction similar to the mass. However, there is no one difference between mass and charge. Mass of a body is always positive, whereas charge can be either positive or negative. Proper signs have to be used while adding the charges in a system. For example, the total charge of a system containing 5 charges plus 1 plus 2 minus 3 plus 4 and minus 5 in some arbitrary unit is plus 1 plus 2 plus minus 3 plus 4 plus minus 5 is equal to minus 1 in the same unit. Conservation of electric charge. Just like energy and mass can be conserved, the electric charges can also be conserved. The law of conservation states that the total charge of an isolated system remains constant, that is, charges can neither be created nor destroyed. Quantization of electric charge. The principle of quantization of electric charge states that in nature There is the smallest amount of charge, and all other charges are integral multiples of this smallest unit. That is, if E is the minimum charge, then the total charge on the body is equal to NE, where N is an integer. This fact that electric charge is quantized was first suggested by experimental laws of electrolysis discovered by Faraday and then by Millikan. In chemical electricity and magnetism, quantization of charge is completely ignored because the quantum of charge E is very small. In microscopic level, where the charges involved are of the order of few powers of tens or hundreds of E, quantization of charge cannot be ignored. Note 1. The magnitude of the smallest unit of charge is 1.6 into 10 power minus 19 coulombs. 2. The total charge on a body is plus Ning or minus Ning. 3. A charged body cannot possess fractional charge. 4. The total charge on a body is equal to the algebraic sum of the individual charges present in the body. 5. A body is electrically neutral if it has equal number of positive and negative charges. 6. The charge is quantized, which means that the charge exists in the form of discrete packets. Coulombs Law. Coulombs Law states that the electrostatic force between two electric charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. If Q1 and Q2 are 2-point charges separated by a distance r, the electrostatic force F between the charges is given by F is directly proportional to Q1 Q2 by r square, or F is equal to K of modules of Q1 Q2 by r square, where K is a positive constant called Coulomb's constant. This value depends on the medium between the two charges. A. If the charges are in vacuum, then in SI units, K is equal to 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of space. The value of epsilon naught is equal to 8.854 into 10 power minus 12 Coulomb square per Newton meter square, which was obtained by experiments. Thus K is equal to 8.988 into 10 power 9 Newton meter square per Coulomb square. Subtopics: Unit of charge, Coulomb. Vector form of Coulomb's law. Unit of charge, Coulomb. The unit of charge is Coulomb and is denoted by C. 1 coulomb of charge is that charge which, when placed 1 meter from another charge in vacuum, experiences an electrical force of repulsion of magnitude 9 into 10 power 9 newtons. B. If the charges are immersed in matter, then epsilon naught is replaced by EA, quantity characteristic of the matter involved. Then K is equal to 1 by 4 pi epsilon naught. The number epsilon naught is called absolute electric permittivity of the dielectric medium. In vacuum, epsilon is equal to epsilon naught, and the ratio epsilon r is equal to epsilon by epsilon naught is known as dielectric constant or relative permittivity. So Coulomb's law is written as F is equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. Vector form of Coulombs law. A. If Q1, Q2 greater than 0, that is either both Q1 and Q2 are positive or both are negative, then the charges repel each other. If Q1, Q2 less than 0, that is, if the charges are dissimilar, then the charges attract each other. If F2, 1 is the force exerted on the charge Q2 by Q1 and Q1, Q2 greater than 0, then F2, 1 bar is equal to K into Q1, Q2 by R square into R2, 1 cap. When R2, 1 cap is the unit vector pointing from Q2 to Q1, similarly, if F1, 2 bar is the force exerted on charge Q2 by Q1 and Q1, Q2 greater than 0, then F1, 2 bar is equal to K into Q1, Q2 by R square R1, 2 cap, where R12 cap is the unit vector pointing from Q2 to Q1. But we know that R2, 1 cap is equal to minus R1, 2 cap. Therefore, F1, 2 bar is equal to K into Q1, Q2 by R square of minus R2, 1 cap is equal to minus K Q1, Q2 R square minus R2, 1 cap is equal to minus F2, 1 bar. That is, F1, 2 bar is equal to minus F2, 1 bar. Thus, Coulomb's law agrees with Newton's third law. Forces between multiple charges. Coulomb's law describes only the interaction of two-point charges. Experiments show that when two charges exert forces simultaneously on a third charge, the total force acting on that charge is the vector sum of the forces that the two charges would exert individually. This important property is known as the superposition principle. This principle holds good for any number of charges. Subtopic: the superposition principle. The principle states that when a number of charges are interacting, the resultant force on a particular charge is given by the vector sum of the forces produced by the individual charges. If several point charges Q1, Q2, Q3 and so on, Qn simultaneously exert electric force on the charge Q, then the net force on Q is obtained by taking the vector sum of the individual forces. Mathematically, it can be stated as F bar is equal to F1 bar plus F2 bar plus so on plus Fn bar, whereas the net force and F1 bar, F2 bar, so on are the individual forces exerted by Q1, Q2, so on, Qn on the qth charge. This is the superposition principle of electric forces, also true for electric fields. Considering a system of point charges Q1, Q2, and so on, Qn, and if the position vectors are given by R1 bar, R2 bar, so on, Rn bar, then the forces experienced by any one charge due to the other charges can be written mathematically as follows. F1 bar equals to F1 2 bar plus F1 3 bar plus F1 4 bar. F1 bar, where F1 is the net force experienced by the Q1 charge and F1 2 bar is the force experienced by Q1 due to Q2. F1 3 bar is the force experienced by Q1 due to Q3, etc. Then in general, it can be written as F1 bar is equal to sigma F, where J not equal to 1. Since a charge does not exert a force on itself, combining Coulombs law with superposition principle, the equation 1 can be written as F1 bar equals to 1 by 4 pi epsilon naught into Q1 Q2 by R1 2 square into R1 2 cap plus Q1 Q3 by R1 3 square into R1 3 cap, so on, plus Q1 Qn by R1 n square into R1 n cap. F1 bar is equal to Q1 by 4 pi epsilon naught sigma Qj by R1j square R1j cap. The vector sum are obtained by using parallelogram law of vectors. All of electrostatics is basically the consequence of Coulomb's law and the superposition principle. Electric field. The electric field or electric field strength is the electrostatic force acting on a unit positive test charge placed at that point if F bar is the electrostatic force experienced by a test charge Q at a point. Then the electric field intensity at that point is given by E bar is equal to F bar by Q. A SI unit of electric field intensity is Newton per Coulomb. Note: if the test charge is not small, then the electric field may be affected by the test charge, and hence we modify the above equation as follows. E bar is equal to limit Q tends to 0 F bar by Q. Subtopics: electric field due to a point charge, electric field due to a system of charges, physical significance of electric field. Electric field due to a point charge. Consider a charge Q at the origin of the coordinate system. Let a test charge Q be placed at a distance r from the origin. If F bar is the force exerted by Q on Q, then according to Coulomb's law, F bar is equal to 1 by 4 pi epsilon naught Q by R square R cap, equation 1. If R cap is a unit vector in the direction of R, electric field E bar is equal to F by Q. E bar is equal to 1 by 4 pi epsilon naught Q by R square Q R cap. E bar is equal to 1 by 4 pi epsilon naught Q by R square R cap. The magnitude of the electric field intensity due to a point charge is E is equal to 1 by 4 pi epsilon naught Q by R square. Electric field due to a system of charges. Consider a system of charges Q1, Q2, and so on, Qn, placed at distances R1, R2, and so on, Rn, with respect to some origin. Then the electric field intensity due to all these charges at a point is found out using the principle of superposition. Let E1 bar, E2 bar, E3 bar, and so on, En bar be the electric field intensity due to the number of charges Q1, Q2, and so on, Qn. Then the resultant electric intensity E bar at that point due to these charges is given by the superposition theorem. E1 bar is equal to E1 bar plus E2 bar plus E3 bar plus and so on En bar. Electric field intensity due to the nth charge is En bar is equal to 1 by 4 pi epsilon naught Qn by Rn square R cap. Magnitude of the electric field intensity is given by the equation En is equal to 1 by 4 pi epsilon naught Qn by Rn square. Physical significance of electric field. Calculations of electric field intensity are of tremendous importance due to the technological applications of electric forces. To determine the trajectories of electrons in a TV tube, in an accelerator used in cancer radiotherapy, or of charged particles in a semiconductor electronic device, we have to know the detailed nature of electric field acting on the charges. Thus, electric field helps us determine the electrical environment of a system of charges. Electric field lines. Michael Faraday, 1791 to 1867, introduced the idea of lines of forces. Electric field lines. Field lines give us a means of representing the electric field pictorially. The electric field vector E is tangent to the electric field line at each point. The line has a direction that is the same as that of the electric field vector. The number of lines per unit area through a surface perpendicular to the lines is proportional to the magnitude of the electric field in that region. Electric field lines. General. The density of lines through surface A is greater than through surface B. The magnitude of the electric field is greater on surface A than B. The lines at different locations point in different directions. This indicates the field is non-uniform. Electric field lines. Positive point charge. The field lines radiate outward in all directions. In 3 dimensions, the distribution is spherical. The lines are directed away from the source charge. The positive test charge would be repelled away from the positive source charge. Electric field lines. Negative point charge. The field lines radiate inward in all directions. The lines are directed toward the source charge. The positive test charge would be attracted toward the negative source charge. Electric field lines. Dipole. The charges are equal and opposite. The number of field lines leaving the positive charge equals the number of lines terminating on the negative charge. Electric field lines. Like charges. The charges are equal and positive. The same number of lines leave each charge since they are equal in magnitude. At a great distance, the field is approximately equal to that of a single charge of 2q. Electric field lines. The positive charge is twice the magnitude of the negative charge. 2 lines leave the positive charge for each line that terminates on the negative charge. At a great distance, the field would be approximately the same as that due to a single charge of positive q. Electric field lines. Rules for drawing. the lines must begin on a positive charge and terminate on a negative charge. In the case of an excess of one type of charge, some lines will begin or end infinitely far away. The number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. No two field lines can cross. Electric flux. The electric flux through a surface held inside an electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface. Electric flux is a scalar quantity and is denoted by phi. Consider flow of a liquid with velocity v through a small flat surface ds in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing the area per unit time v ds and represents the flux of liquid flowing across the plane. If the normal to the surface is not parallel to the direction of flow of liquid, that is, to v bar, but makes an angle theta with it, the projected area in a plane perpendicular to v is v ds cos theta. Therefore, the flux going out of the surface ds is v bar dot n cap ds. For the case of the electric field, we define an analogous quantity and call it electric flux. We should, however, note that there is no flow of a physically observable quantity, unlike the case of liquid flow. In the picture of electric field lines described above, we saw that the number of field lines crossing a unit area placed normal to the field at a point is a measure of the strength of electric field at that point. This means that if we place a small planar element of area delta S normal to E bar at a point, the number of field lines crossing it is proportional to E delta S. Now suppose we tilt the area element by angle theta. Clearly, the number of field lines crossing the area element will be smaller. The projection of the area element normal to E is delta S cos theta. Thus, the number of field lines crossing delta S is proportional to E delta S cos theta. When theta equals to 90 degrees, field lines will be parallel to delta S and will not cross it at all. Thus, the area element vector delta S bar at a point on a closed surface equals delta S n cap, where delta S is the magnitude of the area element and n cap is a unit vector in the direction of outward normal at that point. We now come to the definition of electric flux. The electric flux delta phi through an area element delta S bar is defined by delta phi equals to E bar dot delta S bar equals to E delta S cos theta, equation 1, which, as seen before, is proportional to the number of field lines cutting the area element. The angle theta here is the angle between E bar and delta S bar. For a closed surface, with the convention stated already, theta is the angle between E bar and the outward normal to the area element. Notice, we could look at the expression E delta S cos theta in two ways. E delta S cos theta that is, E times the projection of area normal to E bar, or E perpendicular to delta S, that is, component of E bar along the normal to the area element times the magnitude of the area element. The unit of electric flux is Newton meter square per Coulomb. The basic definition of electric flux given by equation 1 can be used in principle to calculate the total flux through any given surface. All we have to do is to divide the surface into small area elements, calculate the flux at each element and add them up. Thus, the total flux phi through a surface S is phi approximately sigma E bar dot delta S bar equals to sigma E bar dot delta S bar, equation 2. The approximation sign is put because the electric field E bar is taken to be constant over the small area element. This is mathematically exact only when you take the limit delta S tends to 0 and the sum in equation 2 is written as an integral. Electric dipole. Electric dipole is a pair of point charges with equal magnitude and opposite in sign separated by a distance. Many physical systems from molecules to TV antenna can be described as electric dipoles. A water molecule is an example of an electric dipole. Even though the water molecule as such is neutral, the chemical bonds within the molecule causes displacement of charges. This displacement of charges creates a dipole with a negative charge on the oxygen end and a net positive charge on the hydrogen end. If water molecules were not electric dipoles, water would have been a poor solvent. Subtopics. The field of an electric dipole. A. For points on axial line. B. For points on the equatorial line. The field of an electric dipole. Electric field produced by a dipole is known as dipole field. Let plus Q and minus Q be equal and opposite point charges separated by a small distance 2L. The strength of an electric dipole is measured by a vector quantity known as electric dipole moment P bar, which is the product of the charge and separation between the charges, that is, P bar is equal to Q into 2L. The direction of P bar is always from negative to positive. The SI unit of dipole movement is Coulomb meter. A. For points on the axial line. The axial line of a dipole is the line passing through the positive and negative charges of the electric dipole. Consider a system of charges minus Q and plus Q separated by a distance 2a. Let P be any point on an axis where the field intensity is to be determined. Electric field at P EB due to plus Q. EB is equal to 1 by 4 pi epsilon naught Q by BP whole square along BP is equal to 1 by 4 pi epsilon naught Q by R minus A whole square. Electric field at P due to minus Q of EA. EA is equal to 1 by 4 pi epsilon naught Q by AP square along PA is equal to 1 by 4 pi epsilon naught Q by R plus A whole square. Net field at P is given by EP is equal to EB minus EA is equal to 1 by 4 pi epsilon naught of Q by R minus A whole square minus Q by R plus A whole square. Simplifying, we get EP is equal to Q by 4 pi epsilon naught for AR by R square minus A square whole square. EP is equal to 2 Q by 4 pi epsilon naught 2 R by R square minus A square whole square. 2AQ is equal to P. K is equal to 1 by 4 pi epsilon naught, or EP is equal to 2 kpr by R square minus A square whole square along BP. As special case, if 2A much less than R, EP is equal to 2 kp by R cube along BP. B. For points on the equatorial line. An equatorial line of a dipole is the line perpendicular to the axial line and passing through a point midway between the charges. Electric field intensity due to a dipole at a point lying on the perpendicular bisector of a dipole. Consider a dipole consisting of minus q and plus q separated by a distance 2a. Let P be a point on the equatorial line. EA bar is equal to 1 by 4 pi epsilon naught q by AP square along PA. EA bar is equal to 1 by 4 pi epsilon naught q by R square plus A square. EB bar is equal to 1 by 4 pi epsilon naught q by BP square along PD. EA bar is equal to 1 by 4 pi epsilon naught q by R square plus A square. The resultant intensity is the vector sum of the intensities along PA and PB. EA and EB can be resolved into vertical and horizontal components. The vertical components of EA and EB cancel each other as they are equal and oppositely directed. It is the horizontal components which add up to give the resultant field. E is equal to EA cos theta plus EB cos theta. EA is equal to EB is equal to 1 by 4 pi epsilon naught q by square root of R square plus A square whole square is equal to 1 by 4 pi epsilon naught q by R square plus A square. E is equal to 2 EA cos theta. Substituting cos theta is equal to A by R square plus A square power 1 by 2 in the above equation. E is equal to 2 EA cos theta is equal to 2 by 4 pi epsilon naught q by R square plus A square. A by R square plus A square power 1 by 2. E is equal to Kp by R square plus A square power 3 by 2 along Px, as 2Qa is equal to P. As a special case, if 2A much less than R, then E is equal to Kp by R cube along Px. We find that at very far off points, that is 2A less than R, electric intensity at an axial point is twice the electric intensity on the equatorial line. Dipole in a uniform external field. An electric field is said to be uniform if the electric field strength at every point in the field is the same. Subtopics. Uniform external field. Force on a dipole in a non-uniform electric field. Uniform external field. Consider a permanent dipole of dipole moment P in a uniform external field E, which implies that P does not depend E, nor it is included due to E. The force on Q is QE and on minus Q is minus QE, and net force on dipole is 0. However, the charges are separated, so the force act on different points, giving rise to a torque twisting force on the dipole. When net force is 0, torque is independent of the origin. Its magnitude equals the magnitude of each force multiplied by perpendicular distance between the two antiparallel forces. That is, magnitude of torque tau is equal to QE into 2a sin theta is equal to 2q a e sin theta. Tau is equal to p e sin theta, where p is equal to 2qa. In vector notation, tau is equal to p bar into e bar are assumed to be in the plane of the paper. From the above, it is found that an electric dipole placed in uniform electric field experiences a torque which aligns the dipole parallel to the direction of the electric field. Forces on a dipole in a non-uniform electric field. Forces on a dipole in a non-uniform electric field. When electric field is not uniform, the net force will be non-zero. There will also be torque on the system. When P is parallel or antiparallel to E, the net torque is 0. But there is a force on the dipole E which is not uniform. It is seen that when P is parallel to E, dipole has a net force in the direction of increasing field, and when P is antiparallel to E, the net force on dipole is in the direction of decreasing field. Force depends on the orientation of dipole moment with respect to the external field. Electric field of a continuous charge distribution. Very often, the distances between charges in a group of charges are much smaller than the distance from the group to some point of interest, for example, a point where the electric field is to be calculated. In such situations, the system of charges is smeared out or continuous. That is, the system of closely spaced charges is equivalent to a total charge that is continuously distributed along some line over some surface or throughout some volume. First, we divide the charge distribution into small elements, each of which contains a small charge delta Q as shown in figure. Next, we use equation to calculate the electric field due to one of these elements at a point P. Finally, we evaluate the total field at P due to the charge distribution by summing the contributions of all the charge elements, that is, by applying the superposition principle. The electric field at P due to one element carrying charge delta Q is delta E is equal to K delta Q by R square R cap, where R is the distance from the element to point P and R cap is a unit vector directed from the charge element toward P. The total electric field at P due to all elements in the charge distribution is approximately E is equal to K sigma delta Qi by Ri square Ri cap. where the index I referred to the ith element in the distribution because the charge distribution is approximately continuous. In the limit delta Qi tends to 0, E is equal to K. Limit Qi gives rise to naught sigma delta Qi by Ri square Ri cap is equal to K integration of dq by R square R cap, where the integration is over the entire charge distribution. This is a vector operation and must be treated appropriately. We illustrate this type of calculation with several examples in which we assume the charge is uniformly distributed on a line, on a surface, or throughout the volume. When performing such calculations, it is convenient to use the concept of a charge density along with the following notations. If a charge Q is uniformly distributed throughout a volume V, the volume charge density ρ is defined by ρ is equal to Q by V, where ρ has units of Coulomb per meter cube. If a charge Q is uniformly distributed on a surface of area A, the surface charge density sigma is defined by sigma is equal to Q by A, where sigma has units of coulombs per meter square. If a charge Q is uniformly distributed along a line of length L, the linear charge density lambda is defined by lambda is equal to Q by L, where lambda has units of coulombs per meter. Gauss Theorem. We have already learned to find the electric field intensity due to a charged conductor using Coulombs Law. Gauss Theorem can also be used to calculate the electric field intensity provided there is a symmetry in the charge distribution. Can be considered as an alternative to Coulombs Law for expressing the relationship between electric charge and electric field. This theorem was formulated by a German mathematician Carl Friedrich Gauss. Gauss' theorem states that the total electric flux through any closed surface is proportional to the total electric charge inside the surface. Total electric flux is directly proportional to Q. Phi is equal to 1 by epsilon naught Q. But we have already obtained the relation phi is equal to surface integration of E bar dot dA bar. Phi is equal to surface integration of E bar dot dA bar is equal to Q by epsilon naught. Therefore, phi is equal to Q by epsilon naught. This means the electric flux is independent of the radius of the surface, but only depends on the charge enclosed by the surface. Subtopics. Proof for Gauss theorem. Let case 1. When Gaussian surface is spherical in shape, a positive charge Q be placed at the center of an imaginary spherical surface of radius r as shown in figure. The electric flux is equal to E bar dot dA bar. d phi is equal to E dA cos theta, equation 2. By symmetry, the field due to the charge plus Q is radial and E is perpendicular to the sphere and is directed along the normal to the surface. So the angle between the normal and the electric intensity is 0. That is, d phi is equal to E dA cos 0. d phi is equal to E dA. Surface integration of d phi is equal to surface integration of E dA is equal to surface integration of Q by 4 pi epsilon naught R square dA is equal to Q by 4 pi epsilon naught R square, 4 pi R square. A is equal to 4 pi R square. Phi is equal to Q by epsilon naught, which is nothing but the mathematical representation of Gauss theorem. Case 2. When Gaussian surface is not spherical in shape, the total electric flux is surface integration of E bar dot dA bar is equal to surface integration of Q by 4 pi epsilon naught R square into dA cos theta is equal to Q by 4 pi epsilon naught surface integration of dA cos theta by R square is equal to Q by 4 pi epsilon naught surface integration of d omega, where d omega is a solid angle subtended by the area dA at the point, that is, dA cos theta by R square is equal to d omega. Surface integration of d omega is equal to 4 pi is the solid angle subtended at 0 by the closed surface. Surface integration of E bar dot dA bar is equal to Q by 4 pi epsilon naught. 4 pi is equal to Q by epsilon naught, which is nothing but Gauss theorem. Application of Gauss theorem. Gauss theorem can be used to calculate the electric intensity due to an infinitely long straight charged wire, a uniformly charged infinite plane sheet, a uniformly charged thin spherical shell. Subtopics: field due to an infinitely long straight charged wire, field due to a uniformly charged infinite sheet, field due to a uniformly charged thin spherical shell. Case 1. Field inside a hollow conducting sphere. Case 2. Field on the surface of the shell. Case 3. Field at a point outside the spherical shell. Field due to an infinitely long straight charged wire. Consider a thin long charged wire. Let the charge per unit length of the wire be I. To calculate the field at P, we consider a Gaussian surface with wire as axis, radius r and length L as shown in the figure. This Gaussian surface, that is, the cylinder is closed at each end by planes normal to the axis. The electric lines of force are parallel to the end faces of the cylinder, and hence the component of the field along the normal to the end faces is 0. The field is radial everywhere, and hence the electric flux crosses only through the curved surface of the cylinder. If E is the electric field intensity at P, then the electric flux through the Gaussian surface is E into 2πrl. 2πrl is the surface area of the curved part. The charge enclosed by the Gaussian surface is 2. According to Gauss theorem, the total electric flux is lambda L by epsilon naught. Therefore, E 2 pi RL is equal to lambda L by epsilon naught. E is equal to lambda L by 2 pi RL epsilon naught. E is equal to lambda by 2 pi R epsilon naught. E bar is equal to lambda by 2 pi R epsilon naught r cap, where r cap is unit vector. E bar is directed radially outwards if q is positive and radially inwards if q is negative. Note: SI unit of I is field due to a uniformly charged infinite sheet. Let S be the uniform surface charge density of an infinite plane sheet. If x-axis is taken normal to the given plane, then the electric field will not depend on y and z-axis. The Gaussian surface will be a parallelepiped of cross-sectional area A. Only the two faces 1 and 2 will contribute to the flux, whereas the other two faces do not contribute to the total flux as the electric field lines are parallel to them. Flux through the Gaussian surface is equal to 2 The fact that 2 appears as the total flux is due to two faces of parallelepiped which are normal to electric field. According to Gaussian theorem, the total electric flux is sigma A by epsilon naught. Therefore, 2 is equal to sigma A by epsilon naught. E is equal to sigma A by 2A epsilon naught. E is equal to sigma A by 2 epsilon naught. E bar is equal to sigma A by 2 epsilon naught x cap, where x cap is a unit vector along the x-axis. SI unit of S is centimeter square. Field due to a uniformly charged thin spherical shell. Consider a hollow conducting sphere of radius r with its center at O. Let S be its surface density. The field at any point P, outside or inside, depends upon the distance from the center of the spherical shell. Let the distance between the center of the spherical shell and the point be r. Case 1. Field inside a hollow conducting sphere. Consider a thin hollow conducting sphere with radius r. Let Q be the charge on this sphere. To find the field at a point P, draw a Gaussian surface, dotted circle of radius r. Since this surface does not enclose any charge, we have E 4 pi r square is equal to 0 by epsilon naught. Here, E is equal to 0. Case 2. Field on the surface of the shell. When point P lies on the surface of the shell or sphere, R is equal to R. So, E A pi r square is equal to Q by epsilon naught. E is equal to Q by 4 pi r square epsilon naught, pointing radially outwards. Case 3. Field at a point outside the spherical shell. Let the point P be outside the spherical shell. At points outside the sphere, the electric field is radial everywhere because of spherical symmetry. Total electric flux is equal to E 4 pi r square. According to Gauss theorem, the net electric flux is Q by epsilon naught. E 4 pi r square is equal to Q by epsilon naught. E is equal to Q by 4 pi epsilon naught r square. E bar is equal to Q by 4 pi epsilon naught r square r cap. Where r cap is the unit vector, E bar is directed outwards if the charge is positive and is directed inwards if the charge is negative. The electric field in terms of surface charge density. Case 1. Sigma is equal to 0. Hence, E is equal to 0. Case 2. E bar is equal to Q by 4 pi epsilon naught R square R cap. E bar is equal to Q by 4 pi epsilon naught R square R cap. E bar is equal to sigma by epsilon naught R cap. E bar is equal to sigma by epsilon naught R cap. Therefore, Q is equal to sigma 4 pi R square. E is equal to sigma 4 pi R square by 4 pi epsilon naught R square. Case 3. E bar is equal to sigma 4 pi R square by 4 pi epsilon naught R square R cap. E bar is equal to sigma R square by epsilon naught R square R cap.
इस चैनल को लाइक कीजिए, सब्सक्राइब कीजिए और सबको इसके बारे में बताइए।